Today we will explore the 7 main types of stars in the universe. Thank you for watching. Sit back and enjoy. Before we journey through the stellar classification, if you love learning about space and the cosmos, make sure to hit that subscribe button and drop a comment below telling me which type of star fascinates you the most. It really helps the channel grow. Now let's begin our cosmic journey. When you look up at the night sky, every tiny dot of light you see is a star. To us, they all appear as small twinkling specks. But in reality, stars come in an incredible range of sizes, colors, and temperatures. Some burn with an intensity so fierce that they live fast and die young, while others glow faintly but endure for trillions of years, outliving nearly everything else in the universe. Astronomers have found a way to make sense of this diversity by classifying stars into 7 main types based on their temperature and the light they emit. This system is called the spectral classification, and it runs in order from the hottest and rarest stars to the coolest and most common. At first, the order might look unusual: O, B, A, F, G, K, and M. But this sequence reveals the story of stellar physics. At the top end are the blazing O-type stars, massive blue giants so hot they can strip planets bare and burn out in only a few million years. At the bottom are the tiny M-type red dwarfs, dim, cool, and almost invisible to the naked eye, yet so abundant they make up the majority of stars in the universe. Between these extremes lie the familiar stars we know best, including our own Sun, a G-type star. In this video, we'll explore all 7 types of stars, from the mighty blue titans down to the faint red dwarfs. You'll see how their temperatures shape their colors, how their lifespans are determined by mass, and why some types are rare jewels while others quietly dominate the cosmos. So the next time you gaze up at the night sky, you'll know that behind the twinkling lights lies a hidden hierarchy, a cosmic sequence of stars that defines the very fabric of our universe. O-type stars, the blue monsters. At the very top of the stellar classification sit the O-type stars, the rarest and most extreme kind of stars in the universe. If you were to line up every 100,000 stars you could find, only one of them would likely be an O-type. Yet, despite being so scarce, these cosmic giants dominate their surroundings with sheer power. O-type stars burn with surface temperatures of at least 30,000 degrees Celsius, and in some cases even higher than 50,000 degrees. At these extremes, their light shifts into the bluest part of the spectrum, giving them their striking hue. They shine millions of times brighter than our sun, releasing torrents of ultraviolet radiation that ionize entire regions of space. If you've ever seen the colorful glow of a nebula, it is often the handiwork of one of these colossal blue stars energizing the gas around it. Their size is equally staggering. Many O-type stars contain more than 20 times the mass of the sun, and some can reach well over 100 solar masses. With so much fuel, you might expect them to live long and stable lives. But the opposite is true. The greater a star's mass, the faster it burns through its hydrogen supply. O-type stars live in a furious blaze, consuming their reserves in just a few million years. That's a blink of an eye compared to stars like our sun, which can last billions of years. Their short lifespans mean that whenever we find one, we know it must be very young on cosmic timescales, usually born in massive stellar nurseries. They rarely exist in isolation. Instead, they cluster together with other giant stars in regions rich with gas and dust. And because they evolve so quickly, their deaths are as dramatic as their lives. When an O-type star runs out of fuel, it doesn't fade quietly. It ends in a titanic supernova explosion, blasting heavy elements into space and often leaving behind either a neutron star or a black hole. O-type stars also play a crucial role in shaping galaxies. Their radiation and stellar winds carve out cavities in surrounding gas clouds, triggering new waves of star formation. In a sense, they are both creators and destroyers. They stir the cosmos with energy while sealing their fate with every moment they burn. One of the most famous examples is Zeta Puppis, a massive O-type star about 60 times the mass of the Sun and more than 20,000 times as luminous. Another is Rigel, the bright blue star in Orion, which dominates its constellation with dazzling brilliance. These stars are rare jewels, but when they do appear, they reshape their cosmic neighborhoods. So while O-type stars may be fleeting, They leave behind an enduring legacy. They enrich galaxies with the heavy elements needed for planets and life, and their remnants in the form of neutron stars or black holes become some of the most fascinating objects in the universe. They are the blue monsters of the cosmos. Beautiful, dangerous, and essential to the grand story of stars. B-type stars, the blue-white beacons. Just below the mighty O-type giants are the B-type stars, the second hottest category in the stellar classification. They may not reach the extreme conditions of their larger cousins, but they are still among the most powerful stars in the universe. Brilliant blue-white and intensely luminous, they stand out as cosmic beacons visible across vast stretches of space. B-type stars have surface temperatures ranging from about 10,000 to 30,000 degrees Celsius. This places them firmly in the blue-white range of the spectrum, giving them their distinct glow. To the human eye, they shine far brighter than most stars in our sky. In fact, many of the brightest stars we see at night are B-types. Their brilliance isn't just for show. These stars are pumping out immense amounts of ultraviolet radiation, powerful enough to shape the environments around them. Like O-type stars, B-types are relatively rare compared to cooler stars. Though they are far more common than their larger cousins, they make up only a fraction of a percent of all stars in the galaxy. But despite their rarity, they play an outsized role in illuminating the Milky Way. Their radiation often lights up surrounding gas clouds, creating stunning nebulae and star-forming regions that glow vividly in telescopic images. In terms of mass, B-type stars typically range from about 2.5 times the mass of the Sun to as much as 16 solar masses. That makes them less extreme than O-types, but still giant by comparison with most other stars. Their high mass means that, like O stars, they burn through their hydrogen fuel rapidly. While a star like the Sun can live for around 10 billion years, B-type stars only survive for tens to hundreds of millions of years. In cosmic terms, they are still short-lived, but not quite as fleeting as the blazing O-types. Because of their high energy output, B-type stars are often associated with regions of active star formation. They form in dense clusters and stellar nurseries, where their intense radiation and stellar winds can sculpt the clouds of dust and gas around them. This process sometimes helps trigger the birth of new stars while at the same time eroding the very material needed for further star formation. Some of the most famous stars in the night sky fall into this category. Spica, the brightest star in the constellation Virgo, is a massive B-type star system that shines with a blue-white brilliance. Another example is Rigel, often considered an O-type, but in some classifications listed as a late B-type supergiant. Even Vega, one of the most recognizable stars in the summer sky, sits right on the border between A and B types, showcasing how these classifications sometimes overlap. B-type stars are cosmic showpieces, dazzlingly bright yet relatively short-lived. They may not rival the sheer ferocity of O-types, but they are far from ordinary. Their glow reaches across light years, guiding us through the night sky and revealing the active dynamic processes of our galaxy. They are the blue-white beacons of the cosmos, both beautiful to observe and vital to the story of stellar evolution. A-type stars, the brilliant whites. Moving down the stellar sequence, we come to the A-type stars, brilliant white stars that dominate many of the familiar constellations. To the naked eye, they appear pure and dazzling, standing out clearly against the darker backdrop of the night sky. They may not possess the raw power of O or B stars, but their brightness and beauty make them some of the most recognizable stars we can see. A-type stars have surface temperatures between about 7,500 and 10,000 degrees Celsius, which places them hotter than the Sun, but cooler than B-types. Their color appears white to bluish-white, and because of their high temperatures, they emit strong hydrogen absorption lines in their spectra. This makes them particularly important for astronomers who use these signatures to classify and study stars across the galaxy. In terms of mass, A-type stars typically range from about 1.5 to 3 times the mass of the Sun. While that might not sound extreme compared to O or B stars, it still gives them a significant advantage in brightness. Many A-type stars shine tens of times more brightly than the Sun, making them easily visible even from great distances. Their lifespans, however, are shorter than stars like our Sun. While a G-type star can burn steadily for billions of years, A-types typically last for only a few hundred million up to a billion years before exhausting their core hydrogen. This relatively brief existence means they are considered young stars in cosmic terms, and they are often found in regions that have formed more recently within the galaxy. One of the most famous A-type stars is Sirius, the brightest star in our night sky. Just over 8 light-years away, Sirius shines more than 20 times brighter than the Sun and has been a guiding light for navigators and civilizations for thousands of years. Another example is Vega, a brilliant white star in the constellation Lyra, which has played a central role in astronomical history. Vega was the first star to be photographed and is often used as a baseline for calibrating brightness scales. Altair in the constellation Aquila is another A-type star known for its rapid rotation, spinning so fast that it bulges at the equator. Despite their beauty, A-type stars are not the best candidates for hosting life-bearing planets. Their high levels of ultraviolet radiation combined with their shorter lifespans make it difficult for stable long-term planetary environments to develop. But scientifically, they are invaluable. Their clear hydrogen lines provide astronomers with a sort of cosmic yardstick, helping us measure distances and study the composition of stellar populations. A-type stars represent a balance between brilliance and transience. They are luminous enough to dominate our skies yet fleeting when compared to the slower-burning cooler stars that vastly outnumber them. For us on Earth, they are the brilliant whites, the shining jewels that remind us how even stars of modest size can light up the universe with breathtaking clarity. F-type stars, the golden white suns. As we move further down the stellar classification, we encounter the F-type stars, often described as golden white suns. These stars are hotter and brighter than our Sun, yet not as extreme as the brilliant A-types we just explored. In many ways, they represent a middle ground between the larger short-lived stars and the smaller long-lived ones. F-type stars have surface temperatures between about 6,000 and 7,500 degrees Celsius. To our eyes, this gives them a color that falls somewhere between yellow-white and pale gold, a gentle radiance that makes them stand out without the harsh glare of hotter stars. Astronomers value them for their stability as they strike a balance between high energy output and relatively long lifespans. In terms of size, F-type stars typically range from about 1.0 to 1.4 times the mass of the Sun. This modest increase in mass results in a significant jump in luminosity. Many F-type stars shine several times brighter than the Sun, making them easy to spot across interstellar distances. Their lifespans range from about 2 to 4 billion years, shorter than the Sun's 10 billion, but still long enough to allow planetary systems time to evolve. Because of this balance, F-type stars are often considered interesting candidates in the search for habitable worlds. They are stable enough to support planetary development, and their habitable zones, the region where liquid water can exist, are wider than those of cooler stars. However, their stronger radiation output could pose challenges for life as we know it. The increased levels of ultraviolet light might strip planetary atmospheres or make the surface environment more hostile. Still, many scientists view them as potential hosts for advanced planetary systems, perhaps even ones where life could thrive under protective atmospheres or oceans. Some of the brightest stars in our night sky belong to this category. Procyon, the brightest star in the constellation Canis Minor, is a well-known F-type that shines less than 12 light-years away from us. Another notable example is Gamma Virginis, a binary pair of F-type stars orbiting each other in a complex celestial dance. These nearby stars provide astronomers with valuable laboratories for studying stellar physics and planetary formation. What makes F-type stars particularly intriguing is that they bridge the familiar with the extraordinary. They are not as fleeting as the hot blue stars, yet they radiate more intensely than stars like our Sun. Their golden white glow symbolizes a delicate balance between brilliance and endurance, a reminder that not all stars live at the extremes. F-type stars may not dominate the galaxy in numbers, but they hold a special place in our understanding of stellar diversity. They shine as golden white suns, embodying both the promise of stability and the allure of possibility in the search for life beyond Earth. G-type stars, the yellow dwarfs like our Sun. Among the 7 main types of stars, none are more familiar to us than the G-type stars, often called yellow dwarfs. Though the name suggests something ordinary, these stars are far from insignificant. They include our own Sun, the star that provides Earth with warmth, energy, and the conditions necessary for life. G-type stars have surface temperatures ranging from about 5,200 to 6,000 degrees Celsius, placing them in the yellow portion of the spectrum. Their light, however, is not purely yellow. When viewed from space without Earth's atmosphere scattering it, the Sun actually appears closer to white. But the yellow tint seen from Earth has led to their common nickname, yellow dwarfs. These stars typically range from about 0.8 to 1.1 times the mass of the Sun. While this may not seem like a large variation, the differences in brightness and lifespan can be dramatic. A G-type star like the Sun shines steadily for billions of years with a total lifespan of around 10 billion years. This long period of stability makes them excellent hosts for planetary systems, giving planets like Earth enough time to form and evolve complex ecosystems. In terms of numbers, G-type stars are relatively uncommon compared to cooler types. They make up only about 7% of all stars in the Milky Way. Yet despite their modest population, they are vital for our understanding of the universe, since they provide the environments most familiar to us. The Sun is, of course, the most famous example of a G-type star. Its stable energy output has allowed life to flourish on Earth and its habitable zone. The narrow band around the star where liquid water can exist has made our planet uniquely suited for biology. But the Sun is not alone. Alpha Centauri A, part of the nearest star system to Earth, is also a G-type star, slightly larger and brighter than our own. Tau Ceti, another nearby G-type, has been studied extensively for its potential planetary system. G-type stars are not eternal. Over time, they consume the hydrogen in their cores, gradually heating and expanding. Eventually, a yellow dwarf like the Sun will swell into a red giant, engulfing nearby planets and transforming dramatically before ending its life as a white dwarf. But for billions of years before that, they remain remarkably steady, offering a window of stability that allows life the chance to emerge. What makes G-type stars so significant is not just their role in stellar classification, but their connection to us. For humanity, the story of stars is anchored by the Sun, a single G-type star that sustains our world. In the grand tapestry of the cosmos, they may be just one category among many, but for us they represent the warm heart of home. K-type stars, the orange dwarfs. Just below the G-type stars in temperature are the K-type stars, often called orange dwarfs. They are cooler and dimmer than the Sun, yet they possess qualities that make them some of the most intriguing stars in the galaxy. With their soft orange glow and long lifespans, they are sometimes thought of as the quiet overachievers of the stellar world. K-type stars have surface temperatures between about 3,700 and 5,200 degrees Celsius, giving them their characteristic orange hue. They are smaller than the Sun, typically ranging from about 0.6 to 0.9 solar masses. This modest size means they shine less brightly than G-type stars. But what they lack in brilliance, they make up for in endurance. One of the most remarkable traits of K-type stars is their longevity. While our Sun will last about 10 billion years, K-type stars can live for 20 to 30 billion years and in some cases even longer. This extraordinary stability gives their planetary systems much more time to evolve, making them highly interesting in the search for habitable worlds. Their habitable zones are closer in than those around G-type stars, but wide enough to potentially host planets where liquid water could exist. The reduced radiation output of K-type stars also makes them less harsh than hotter stars, offering a gentler environment for planetary atmospheres. For this reason, some astronomers suggest that K-type stars might be the best places to search for advanced civilizations. Long-lived stars that provide ample time for life to develop and thrive. Several nearby stars fall into this category. Epsilon Eridani, just over 10 light-years away, is a young K-type star with a known planetary system and debris disk, making it a favorite target for study. Arcturus, the brightest star in the constellation Boötes, is a more evolved example. It began as a K-type dwarf before expanding into a giant. These stars remind us that orange dwarfs are both common and diverse, offering many opportunities to explore stellar evolution. K-type stars make up roughly 12% of the stars in our galaxy, more numerous than G-types, but less so than the abundant red dwarfs that come next. They occupy a sweet spot in the stellar hierarchy, bright enough to be seen across interstellar distances, but long-lived enough to provide stable conditions for billions upon billions of years. Though they may not shine as brilliantly as the blue-white stars higher on the scale, their quiet persistence makes them uniquely fascinating. K-type stars are the orange dwarfs of the cosmos. Steady, enduring, and perhaps the most promising hosts for life beyond Earth. M-type stars, the red dwarfs. At the end of the stellar classification, we find the M-type stars, better known as red dwarfs. They are the smallest, coolest, and faintest of the main sequence stars. Yet, despite their modest appearance, they are by far the most common stars in the universe. In fact, more than 70% of all stars in the Milky Way are red dwarfs. Red dwarfs have surface temperatures between about 2,400 and 3,700 degrees Celsius, much cooler than our Sun. Their light shifts toward the reddish end of the spectrum, giving them their name. But to the naked eye, most red dwarfs are too dim to see at all. Even the closest one, Proxima Centauri, just over 4 light-years away, is invisible without a telescope. In terms of size, M-type stars can be as small as 1/10 the mass of the Sun. Their luminosity is tiny in comparison, sometimes only a fraction of a percent of the Sun's brightness. Yet, what they lack in energy, they make up for in longevity. Red dwarfs burn their fuel with incredible efficiency, allowing them to live not for billions, but for trillions of years. That means no red dwarf has ever reached the end of its life in the history of the universe. There simply hasn't been enough time. This staggering lifespan makes them fascinating when it comes to the possibility of life. Their habitable zones are much closer in than those of larger stars, sometimes so close that a planet orbiting within it may be tidally locked with one side always facing the star. This creates challenges such as extreme temperature differences and the potential for powerful stellar flares. Yet many exoplanets discovered so far orbit red dwarfs simply because these stars are so numerous. The famous TRAPPIST-1 system with 7 Earth-sized planets is centered on a small M-type star. Another well-known example is Barnard's star, just 6 light-years away, which has been the subject of study for over a century. These nearby red dwarfs remind us that while they may be faint, they are also abundant, forming the invisible scaffolding of our galaxy. Red dwarfs may not dazzle the eye, but their quiet persistence makes them the true survivors of the cosmos. Long after stars like the Sun have expanded and died, the red dwarfs will still be burning slowly, casting their dim glow across an ancient universe. They are the unassuming majority, the cosmic embers that will outlast almost everything else in existence. From the blazing O-type giants to the faint, quiet red dwarfs, the diversity of stars is nothing short of extraordinary. Each type plays its own role in the grand tapestry of the cosmos. Some living fast and ending in violent supernovae, others burning slowly and steadily for trillions of years. Our own Sun, a modest G-type star, sits right in the middle. It is not the largest, nor the smallest, not the brightest, nor the dimmest. And yet, it is perfectly balanced to sustain life on a small rocky planet orbiting at just the right distance. When we look up at the night sky, we are not only seeing points of light, we are seeing entire categories of stars, each with its own story written in temperature, mass, and lifespan. Understanding these 7 types of stars helps us appreciate both the fragility and resilience of the universe. Some stars are fleeting fireworks, others are eternal embers, but together they shape galaxies, forge elements, and light the way for future worlds. So the next time you gaze at the night sky, remember those twinkling lights are not all the same. Each one is a unique cosmic engine, and without them there would be no planets, no life, and no us. I want to thank you very much for watching. Feel free to share your thoughts on the different types of stars and today's video in the comments. Which stellar type do you find most fascinating? The blue monsters or the eternal red dwarfs? Also feel free to leave a thumbs up to help support the channel, and subscribe if you'd like to see more videos like this in the future. Thanks again and be well.